Good morning, it's Jeremy. It's Friday, June the 20th, and I'm just down at the tip of Trillium Park at Toronto Harbourfront. And I'm going to make a video today about doing a fix. We've got the sun over here, and we've got the moon over here, somewhere up there. So we're just taking measurements now. The sun's just inside Toronto Island there. I'm just going to wait another half hour till it goes on the horizon. The moon, I've got lots of readings already. So we'll just look at the equipment here. So this is the equipment we're going to be using today. I've got my Tamiya sextant. I've got some sunshades for the sun, notebook here, and I've got a Sunto global compass here just to take some azimuths. Okay, so we're just looking at the results of June 20th when I took the various sightings. So I took several sun sightings and I took several moon sightings. The problem I noticed was that on the horizon there was a fair amount of it's kind of a mixture of fog and smoke from the forest fires. So my sightings weren't all that good. This was the best sun sighting at 11:58, and since I knew my location, I was sitting on a bench on Trillium Park, so I checked the location in Google Earth. I also checked it using my iPhone and GNSS receiver, so I knew my location. So I was able to work out what the error was in the measurements. Anyways, that was my best sun sighting. 63 degrees 41 minutes at 11:58:10. Now it's daylight savings time, so UTC is 4 hours on top of that, so that's 15:58:10, and that was my best moon sighting at 15:13:10, and that was the error. That's what it should have been. So 5.7 minutes and 7.6 minutes off there. So if you take the square root of that squared plus that squared, you get an approximate idea of the error. Anyways, the whole purpose of this was just to get practice with the sextant and using the sight reduction methods. So you got to do that every so often. Otherwise it's easy to forget. I also find it's good to do it several different ways because it's very, very easy to make a mistake. If you're using, for instance, NAO, you've got to make 4 table lookups, and the variables on each side, they can have two different types. You can have, let's say, A and F or whatever, and it's very easy to make a mistake. But when you do several methods, you can catch yourself out and make sure that everything's okay. All right, so once I had the measurements, the next thing you have to do is there's the nautical almanac for June the 20th. So my measurements were between, let's say, 1500 and 1600. So what you do is you linear interpolate the time between that, and then you get the various GHA and DEC for the sun and for the moon. So those are my reductions there. Incidentally, all these details are in the blog post. So there's my HS. I get HA by taking HS and subtracting, there's the dip angle, and adding. Now the index error was 2 minutes off, so you add it. So once you have HA, then you go to HO. So there's the refraction, the semi-diameter, and the PA. So that's how you get the HO, and there's the HC. Now, in terms of refraction, what I did is I have some script files in Psychoslab. Psychoslab is a math program. So there I worked out the dip angle. That's the height of eye down at Trillium Park was about 5 meters above the water. And that's the dip angle for 5 meters. And that's the refraction, sun refraction. And that's the moon refraction. And that's the PA. You can also get their formulas in the Nautical Almanac for calculating all of these. So those particular values I use in the sight reductions here. So at the end of the day, then I have an HO, I've got an HC, I've got rho, which is the difference between HO and HC for the Mark-St. Hilaire method, and I've got an azimuth. And I've also got the GHA and the deck. Now you can use a geometric solution, and that's what I've done here. So basically, once you've worked out the moon geometric position and the sun geometric position there, that's the GHA and the deck for the moon and for the sun. That's the North Pole. That's where you are. So this distance here is the co-latitude in radians times the radius of the Earth, which is 6,371 kilometers. That gives you D2. Over here, that's the co-latitude there of that position times the radius of the Earth. That gives you that distance. You know this angle, that's the difference in degrees between the two GHAs. So knowing two sides and the contained angle, you can figure this distance out here. And then you work on this triangle here. You know this distance here is the HO, 90 degrees minus the HO for the moon times RE. And this distance here is 90 degrees minus HO for the sun times RE. And so you've got this side, and this side, so then you can calculate all the angles. And then you work on this triangle here, you know, this distance, and this angle. Then you can work out this distance here. So this distance will give you the latitude and longitude. That's what I worked out here. And for the NAO, let's slide over here. I've got everything on this spreadsheet here. There's those are the two forms for the NAO. So there's the form for the sun, and there's the form for the moon. So basically, what you do is you choose a latitude, your estimated latitude in integral degrees. So it's closest to 44 degrees where we are. And then you choose your longitude such that when you work out the local hour angle, the local hour angle is an integer. So the GHA, for instance, for the sun is 59 degrees, 7.4 minutes. So then you add 7.4 minutes to the longitude. So when you subtract the two, you get an integer number here. And the same thing over there. So basically you get two APs, one assumed position for the sun and one assumed position for the moon. So then you go through the various tables here and you work out what HC is. And you work out HC and you work out ZN, the azimuth. So then you use the Mark-St. Hilaire method. So I've done this over here. So there's, for instance, there's the assumed position for the sun. That's the azimuth to the sun. So you go along here by the intercept. And then at the end of the intercept, this is the Sumner line, or the line of equal altitudes. You go down here, you draw a line down here. And over here, over here, this is the AP for the moon. Same thing, that's the azimuth to the moon. You go down here by the intercept. And at the end there, you draw a Sumner line, which is at right angles to this line here. And where those two intersect there is the fix. So there's my fix. And the same thing you do for AP3270. So there's AP3270. You've got both the sun and the moon on the same form. You do the same trick there with the local hour angle to make sure that it's an integer. So you adjust the longitude a little bit to compensate so the local hour angle ends up as an integer, just as before. And in this particular case, the results are very, very similar to NAO. So the intercept and the azimuths are almost identical, so the fix is identical as well. What I find with AP3270 is the tables are more extensive. So the lookup there is you only have two lookups, and there are not as many possibilities for each axis. So it's a lot harder to make a mistake. So of the two methods, the AP3270 I prefer. Again, it's easier. It's easier because there are only two lookups. So then this is a comparison here. If you come down here, I got a comparison of the various methods of, there's my known position, there's a geometric solution. OpenCPN also has a plugin where you can do a geometric solution just like PsychoSlab, and it gives you an identical result. And NAO and AP3270 give identical results. And then navigational algorithms, again, is very close. So all these methods give you the same thing, which is basically the whole point of all of this. The other thing I want to do was create this spreadsheet so in the future I can use it as a placeholder so I know what I've done, because it's easy to forget everything if you don't practice all the time.